Welcome to another episode of Planet Possible. Each episode in the season, we're getting into the detail behind the really big issues that are critical to the way that we manage our water and environment. You'll hear directly from leading figures across the sector from around the world and practitioners who are making a difference every day through their work. A huge thank you to our season sponsor for Season 3, Binnies. You'll hear a little bit more about Binnies later, and we're really grateful for their support. I'm Niki Roach, and alongside being a passionate advocate for all things water and environment, I'm a fellow of CIWEM. If you're new to Planet Possible, CIWEM is the Chartered Institution of Water and Environmental Management, and our members in over 90 countries are professionals with a breadth and depth of expertise in the topics that are shaping the future of our planet. Across this season, we're getting into the detail of those topics and seeking out the evidence-led views and authentic opinions that help us better understand what's really possible for the planet. And in today's episode, we're exploring forever chemicals, and we've got a great interview coming up. To help unpick this topic, I'm joined by an expert co-host with over 23 years of experience as an environmental consultant, advising multinational and national companies on contaminated land issues in the UK and Australia. His experience includes working on a range of PFAS investigations and assessments, including a really comprehensive assessment at a former coal-fired power station to the north of Sydney. So welcome to the pod, Mark Challoner.
Hi, Niki. Great to speak to you.
So Mark and I are going to listen to our guest interview together, and then we'll discuss our reflections. Our guest interview today is actually with three people, and it's what I can only describe as the best chemistry lesson I've had for a very long time. We'll hear from Dr. Sarah Bwlb, who's the Toxicology Director at Cambridge Environmental Assessments, and Sarah's got expertise in the theory and practice of human health toxicology and risk-based approaches to environmental hazards. Dirk van Look, a bioengineer and senior project manager for RSK, who specialises in soil investigation and remediation, and Andrew Elphinston. And Andrew is the Senior Technical Director at Binnies, and he brings a wealth of expertise in all aspects of potable water treatment. It's great to hear such a rich conversation between Sarah, Dirk and Andrew, and I was particularly interested to hear Sarah describe some of the potential health impacts that are associated with these forever chemicals.
One of their main effects is to cause fertility issues, so reproductive toxicity, and it affects the unborn child, so developmental toxicity. They also cause immunotoxicity, how we respond, our body's response to vaccines, which is quite topical obviously at the moment, to COVID. And they also are endocrine disruptors, which is huge endocrine disruption is very big in the media at the moment.
So Mark, before we hear the interview, can you help set the scene by explaining what forever chemicals are and why we should be interested in them?
Okay, forever chemicals are a set of mostly man-made persistent organic pollutants, which from a regulatory perspective have been defined by the Stockholm Convention. The Stockholm Convention is a sort of multinational agreement to try and eliminate or restrict the use or production of these persistent organic pollutants. And these persistent organic pollutants are or have been used in products that we use every day, like pesticides and solvents and pharmaceuticals and general industrial chemicals. What we mean by persistent organic pollutants is a set of chemicals that are not easily broken down by natural physical, chemical or biological processes, and that are not generally present in the natural environment, i.e. we put them there. So since they're resistant to breakdown, they last a long time in the environment, and because they last a long time in the environment, they continue to have the potential to impact human health and the ecosystems within the environment, and as a result have been termed forever chemicals. Just as a quick comparison, benzene, which is an organic pollutant but is not considered to be a persistent organic pollutant, rapidly breaks down on contact with air and heat, whereas forever chemicals may last years or even decades in the environment without any significant reduction in their concentration or toxicity. A few of the per- and polyfluoroalkyl substances, PFAS, have been listed by the Stockholm Convention as persistent organic pollutants, and PFAS recently, in the last sort of 2 or 3 years, has almost become synonymous with the term forever chemicals.
Well, that's a great intro. Let's get into the interview with Andrew and Sarah and Dirk, and then we'll circle back and hear a little bit more from you. So here's the interview. A very warm welcome, Dirk, Sarah and Andrew, to Planet Possible. So maybe let's start off with you, Dirk. Can you give us a feel for the different types of PFAS?
PFAS is a group of more than 6,000 substances, compounds. The most known are PFOS and PFOA, but there are a lot of PFASs which are not discovered yet and detected yet. So there's a lot, a big group. We talk also about precursors which could degrade into fully perfluorinated compounds. In fact, PFAS are compounds which are organics and which are fluorinated. It's a fluor chemistry. So we have two main groups, which are sulfonates and fluor carboxylates. These are the most common PFAS which are present.
If we think about where we're starting to see these chemicals accumulate, Andrew, if I come to you first, you've got an expertise in water. What are we starting to see?
We're seeing PFAS really everywhere. They are ubiquitous. So the Environment Agency's been looking, I think, from around sort of mid-2000s, 2005, 2007. We found them in borehole sources, surface waters. They tend to be, certainly in boreholes, it tends to have been through the use of what they call AFFF, which is aqueous film-forming foam, which is your firefighting foam that you see. That's been widely used around Air Force or airports and Air Force bases and things, and that's where we see most of the pollution into the aquifers. That's where it's come from, but it is everywhere.
And what about into rivers?
Sources for rivers, I guess leachate from landfill is a common source, and manufacturers, so processes that use it in the manufacturing, either making the chemicals or using the chemicals for whatever purpose. So for stain-resistant furniture, cosmetics, non-stick frying pans, it's used everywhere. So there are lots of companies using it, and yes, it gets out in the effluent from those works. And from sewage works, it ends up at sewage works, and the sewage treatment processes typically don't remove it.
Are there any sewage treatment processes that do remove it?
Not to any degree. You get a small amount of removal with coagulation, so if you've got phosphate removal, if you're dosing ferric compounds to remove phosphate, which is quite common, then you might get some limited removal there. You might get some removal biologically, but it will be minimal because these things are not really biodegradable. Certainly not in the time frames that they would have passing through a treatment works.
Dirk, your expertise is in soils. So what are we starting to see in soils from an accumulation perspective?
PFAS are deposed by emissions of production facilities where they produce PFAS. So it's spread widespread, and it's accumulating in soil, mainly in the top layer. There are some facilities in Belgium and Holland which have contamination at 5 to 10 kilometers around the facility. It's leaching from the topsoil to the groundwater. It's coming into the groundwater, and then it's spreading to rivers, to water supplies, and so on. So it's very mobile. The main issue of PFAS is spreading in the environment. It's not, in fact, accumulating in the soil. It's once it's in the environment, it will spread through the whole environment. You find it everywhere.
If I could just jump in there. So I think in this country, at least, our biggest problem is we don't know how many PFASs are available because we don't measure them. We only measure a handful of chemicals because we don't have analytical techniques for the rest. And I've just finished a big project with the Environment Agency, and we really struggle to get data of what PFAS is and the amount of PFAS in the environment because we just don't measure a huge range of them. We only measure a handful.
Is that because the techniques aren't available to measure others? What's the reason behind us not doing that at the moment, Sarah?
Some of it is the analytical techniques, some of which is who's going to pay for this. So if there's no regulatory driver, then it's a lot of effort, for water companies, for people who are remediating soil. So usually people have to do it because of a regulatory regime, which we don't have at the moment. And we can't have a regulatory regime unless we know what's there. So it's a bit of a chicken and egg situation.
There is the Drinking Water Inspectorate have, in the last couple of years, I wouldn't say tag it on, that's maybe the wrong expression, but it forms part of the risk assessment that all water companies have to do of their raw water sources, treatment process and the final water. So in the last few years, the Drinking Water Inspectorate have made it clear that they're expecting water companies to look at all of their sites on a risk prioritised basis. But they've listed 47 separate PFAS compounds that they want all water companies to look at over a period of time. I think it's the end of next year, to establish just how serious the situation is. And for those sites where higher levels are encountered, then some kind of treatment would be expected, I think. But
then what do you do with that data, though?
Well, I think that at the moment, the intention is that it will help focus minds on what needs to be done. So there are levels in place. The basic level is you need to know more. The next level threshold would be, well, you need to consult with your public health professional. And then the next level is you need to do something about it. You either need to treat it to get it down to a lower level or take that source out of use. So that's the intention, but yeah, quite what levels they should be set at.
That's where I come in, because again, it's back to the chicken and egg thing. So yes, DWI or the water companies can measure something in water. So if I said to you, right, we've got 20 micrograms per litre of PFBA, what does that mean? Then you need me to tell you how toxic that is. But I can only do that if somebody has tested it in an animal. And then they're not going to do that unless somebody's producing it. For it to be in the water, somebody's making it somewhere. So it's very cyclical. Who puts the money in to do the animal test for me to use to tell you guys what 20 micrograms means? So it's all very interrelated.
You're right. But I think this is the first step really in the UK to getting a proper handle on what the situation actually is, because we haven't been as quick off the mark perhaps as the States or Australia or possibly Netherlands as well, or Belgium, Dirk. But I think the UK is perhaps behind the curve a little bit on this. I don't think it's cost them anything particularly, because no one knows quite what to do with it when you find it.
In Belgium last year there was a big issue and PFAS came in the media and it was a political issue. And since then a lot of investigations are carried out in surface water, in soil. There's a huge progress on investigation and on knowledge about the PFAS presence in the environment, and at the same time the authorities needs to regulate better certain issues. This month, even in the United States, the drinking water standards were divided by a factor of 1,000. These are advisory levels, but not enforceable, but they were very severe in comparison with former standards. So this is in continuous evolution, this regulation.
Well, it definitely feels like a very live topic. Sarah, you started to talk about your role as a toxicologist. Can you give us an insight into what the impacts on the body are from these forever chemicals?
Okay, so to start off with, these chemicals are actually quite different to a lot of other chemicals that bioaccumulate, because most other chemicals like dioxins, for example, PCBs, they accumulate in fat. Well, these chemicals don't. So they're quite unique in that respect. And they actually are water soluble. They like protein. Once they get into the body, they tend to go to places like the liver, the blood and the kidney, where there's a lot of proteins. So they don't, whereas most chemicals, like I said, accumulate in the fat. So once they get into the body, they go to the target organs, we call them. And then there's a big difference between the shorter chain PFASs and the longer chain ones, because the shorter chain ones get rapidly excreted from the body. So they're actually less dangerous for us. So the longer chain ones stay in the body longer, so we get a greater body burden, so they are actually more toxic. But the toxic effects, they've got a whole host of toxic effects, depending on short, long chain and different groups. But primarily, one of the main effects is to cause fertility issues, so reproductive toxicity, and it affects the unborn child, so developmental toxicity. They also cause immunotoxicity, how we respond, our body's response to vaccines, which is quite topical, obviously, at the moment, to COVID. Nobody's done that study yet. And they also are endocrine disruptors, which is huge endocrine disruption is very big in the media at the moment. And they also cause liver damage. So they're the main types of toxicities that we're seeing. We're not so bothered about carcinogenicity, although there are some studies coming through that it does cause cancer. But that's not the prime cause, toxicity of these chemicals.
Okay, that's quite a list. So we've heard about where we're finding them and what their impacts are. Let's switch it up and see if there's anything we can do about this. Dirk, once these chemicals are in the soil, is there anything we can do to remedy the situation?
Yes, there are some techniques. The first technique is, of course, excavation of the soil and dispose it in a landfill. But this is not very sustainable because the chemicals are there forever. And the landfill will be there also forever. Another possibility is to incinerate at a very high temperature. but you need a temperature of 1000 degrees, so that is also very costly. And then there are a lot of other innovative techniques which are in development. There's also stabilization of the soil. You can add adsorbents to the soil, for instance, or in groundwater to prevent further spreading, but that is still in investigation. The main solution is the excavation and the landfill and disposal in Belgium and in other countries. Also, another possibility is washing of the soil, and then you get the PFAS on the sludge of the soil, and you can dispose that also to a landfill. That's another possibility. So you clean the soil, 70%, 30% is disposed. But it's a problem of sustainability. Destruction is very costly.
It all sounds expensive and time-consuming. How big is the issue in the soils? Does it feel like a widespread problem?
Yeah, it's not always possible to excavate. It depends if the site is constructed or not. The soil will be transported to the landfill. I think at the moment this is the only solution possible on the short term. On the long term, there should be investigated much more about remediation of soil contamination.
Our season sponsors for Planet Possible are Binnies, who recognise the opportunity that bringing together a breadth of professions creates to be truly amazing. Their engineers, scientists, constructors and environmental professionals collaborate to drive innovation, and Binnies, like Simon, believe that podcasts are a fantastic way to showcase some of the role models, global best practice and innovation that we have across the water and environment sector. We're grateful to Binnies for their support as it enables us to bring Planet Possible to you this season. Andrew, we started to talk earlier about water and wastewater treatment technology. So what else is on the horizon that's being developed or is out there already?
There are processes out there already. Sarah touched on chain length for these compounds, and there she's referring to the number of carbon atoms in the chain. So when we talk about PFOA and PFOS, the O is the octanoic, and that will octane. That's referring to 8 carbon atoms in that molecule, and the number of carbon atoms in that chain determine to some degree how easy or not they are to remove. And something else we haven't touched on really, we haven't mentioned I think, is the fact that these compounds, what's made them so useful is that they have what they call a head and a tail, and the tail is organic. It's got no electrical charge. The head is still organic, but it's got an electrical charge associated with it. An acid is a hydrogen, an H plus ion that breaks away essentially from the molecule, and then you end up with a molecule that is the PFAS molecule with a charged end and an uncharged end. It makes treatment easier in some respects. So the classic treatment process would be granular activated carbon, and that's in use at a lot of surface water works already to remove pesticides, to remove taste and odours, perhaps to reduce disinfection byproducts. So it's widely used, it's widely understood. That would go for the hydrophobic end, so the non-charged end. That will tend to absorb onto the carbon, and that is quite effective. So you're getting 99% removal, better than that, depending on how long you leave it in contact with the carbon for. So that's one approach that is probably the most widespread. Ion exchange, which is like a simple water softener really, and that's actually using both. So you can get conventional ion exchange resins, which will go for the charged end, so the head of this molecule will attach itself to the resin. More bespoke resins can be produced that actually go for both ends, so that the charged end will be removed on one part of the resin, and the water hating end, the hydrophobic end, will attach itself a bit like to a carbon site. And that's better for the short chain, so where you've perhaps only got 4 or 5, 6 carbon atoms in the chain. The carbon's better for the longer chains. The downside with both those processes is that you're removing it from the water, but you're concentrating it on something else. So the carbon ends up now full of PFAS, or likewise the resin does. You can regenerate both, but as Dirk says, you're into his territory then. How do I burn this stuff? What do I do? So at the moment, it tends to be incineration. At least that's the current thinking. That's what would happen to it. It would be incinerated. In due course, the resin could be regenerated. You've then got a liquid stream, which has got this stuff in it. There do seem to be, I think, more methods for destroying PFAS, completely destroying it, breaking this hydrogen fluorine bond, which is it's one of the strongest bonds in chemistry, I think. But you need really high energy at the moment to do that. So yes, two methods there, carbon and ion exchange. The third method that could be used is some kind of membrane, so reverse osmosis perhaps, or nanofiltration. And there, your reject stream, you're perhaps putting through anywhere between 75 and 90% of water goes through the membrane. The remainder comes out as a side stream. And there you've got a liquid stream, which is rich in PFAS. And there are a number of innovative methods for destroying PFAS from liquids, but none of them are cheap. And I think that's the difficulty. It can all be done, but it becomes expensive.
So as we begin to close out, let's talk a bit about regulation. Sarah, from a health perspective, what does the regulatory framework look like for PFAS?
All chemicals that are used or manufactured in Europe have to be registered under REACH. So a lot of PFASs are, and some of them which don't have a registration have what we call the notified classification. So somebody has said, I manufacture this chemical, I think it causes reproductive toxicity. So we have an awful lot of data via the REACH regulations. In terms of the regulations that I work in, and it will touch both on Andrew's work and Dirk's work. So toxicology basically is the foundation of all regulations, because I will tell you what level of these chemicals is safe. And then somebody like Andrew, potentially, or working in the water sphere, will take my number and say, well, this is the amount that's safe, and we will convert that into how much is allowed in water. And then somebody working in soil will take my number and say, we'll convert that into how much soil one can be exposed to. And it also goes across consumer products, food contact materials, food regulations. So basically, toxicology is the anchor point. The number that I will derive, or somebody like me, goes into all these different regulations. But we know from recently, we only have toxicity data for a small number of these chemicals. So we can only regulate a small number of chemicals. So it's a chicken and egg situation. Do toxicologists go and look at the toxicology of these chemicals with the view to regulate? Or does somebody like Dirk or Andrew look to see what's in the environment, look to see what's in water, soil, and then come back to me and say, we've got this in the environment, but we need to know how dangerous it is. So it's a cyclic process.
And Dirk, from your point of view, where do you think we should start on regulation?
Firstly, the authorities, they are establishing standards, regulations for soil contamination and for groundwater contamination. That is in continuous evolution. But then when we have to go further and we have to remediate soil, it's impossible to remediate all the PFAS which are present. So we have to set up some certain criteria based on risk assessment. So what is the use of the site? Which people are there? Are they adults? Are they children? Is it in an industrial area? So all these is included in the risk assessment. Finally, we have to put forward a number or a criteria to execute the remediation. So it's a location specific approach which is taken into account to carry out remediation.
And from a regulatory perspective, are there changes you'd like to see, Dirk?
I think the regulation will become more and more severe. As I just said, the order of magnitude of the standards in the United States are becoming 2 to 3-fold lower. We need more regulation, more criteria, because we need to to set up certain methodology which is not present for the risk assessment. So there's a lot of work to be done in this environment of remediation. We need some more input from the authorities, and there's a lot of uncertainty with the companies. Most companies, they want to know where they are at to, how far they have to go, which are the costs, which is the environmental cost of this new PFAS issue. So the authorities need to regulate more the criteria for impact and risk assessment of the PFAS contamination.
In terms of a regulatory regime, I think there's two big problems in my world. A, the data, because like Dirk said, the numbers are getting lower and lower and lower. I can sit in my office and I can derive any number I want, and I can be really precautionary, because unless I have a visibility of the ultimate goal, like what will these numbers be used for, it's largely irrelevant. So, for example, EFSA have derived tolerable daily intakes, which is a concentration that one can be exposed to over a lifetime without it causing adverse health effects, so safe levels. Dirk's already mentioned the US EPA, they call theirs the same number, a reference dose. So everybody's come up with their different numbers which are really low. But then when you transpose that into water, the safe level in water, the safe level in soil, the safe level in food, consumer products, the levels are so low. It's not technically achievable because we don't have the analytics to measure that low. So I can say, I think a safe level is 1 picogram per kilogram body weight per day. Convert that into a water value, that's 10 picograms per litre. Nobody can measure that low. So that standard is now worthless. So now what we're seeing is, yes, we've got these numbers from America, but America is known to be very risk averse, so their numbers are always low, but they're not pragmatic. You can't measure that. So what I know, WHO is doing is, yes, we're looking at the toxicology. Yes, this is what I want to achieve safety, but we can't remove PFAS to that low level. We can't actually measure that level. So we're going to go up and base the standards on what we call technical achievability. So it's no point having a standard that you can't achieve and you can't measure. And then the other big problem that we see in terms of toxicology is these chemicals. Dirk's mentioned we've got 6,000 odd of these chemicals. We can't go and measure them all. We can't derive a standard from them all because we're not going to go and do animal testing on all of those 6,000. It's just not possible. It's against all the REACH regulations, which is all about combining data and reducing animal testing. So what we need to do, and we've done a lot of work, is grouping these chemicals. They don't appear in any sphere of the environment in isolation. So PFOS and PFOA, 9 times out of 10, will be present together. How do they react together? Is it 1 + 1 = 2? Is it 1 + 1 = 5? So we need to look at grouping approaches. We can use what we call a surrogate marker. So if we know that all the chemicals beginning with a P all act in the same way, we don't need to go and test all these chemicals. We don't need to measure. We just say, right, we've got a key substance that begins with P, and then all the other ones we assume are going to be like that one. So that's a much easier, quicker, cheaper way of doing risk assessment. So we're looking into those aspects, and I think that will move the industry forward, especially in land.
On that note, we probably need to wrap up. This feels like the best chemistry lesson I've ever had from you guys. Thank you to my 3 wonderful guests, Dirk, Sarah and Andrew. So Mark, what are your initial reflections on that interview with Dirk and Sarah and Andrew?
Well, I found it really fascinating. I found that the contribution from Sarah in particular, the way she explained the human health effects and the way that PFAS binds to albumin protein within the body rather than the standard approach for most contaminants, which is to bind onto fatty tissue. So, and as such, the standard way we look at toxicity and the effects of contaminants on the body it's non-standard, it's non-routine. This is something slightly different.
When we talk about forever chemicals, are they just PFAS, PFOS, PFER? Forgive my lack of chemistry here, but is that all that forever chemicals is, or is it broader than that?
PFAS stands for per and polyfluorinated alkyl substances. They are synthetic, i.e. they're man-made, and they've been around since the 1940s. Within the PFAS group, there are 3 particular compounds of concern. They are PFOS, which stands for perfluorooctane sulfonic acid, PFOA, which is perfluorooctanoic acid, and then the most recent one, which has just come to the fore in June 2022, so it's really sort of hot off the press, is the perfluorohexane sulfonic acid. So the two, PFOS and PFOA, have 8 carbon atoms, and the most recent one, the PFHXS, has 6 carbon atoms. The Stockholm Convention has a list of persistent organic pollutants. Currently, PFOA and PFHXS sit in the Annex A, i.e. amongst those pollutants that the parties must eliminate, whereas PFOS sits in Annex B, i.e. in the list of pollutants that the parties must try and restrict.
So, Mark, we've heard a lot about the health impacts from Sarah in the interview. We touched a little bit on the sources of these PFAS group of chemicals, but can you tell me a little bit more about where they're coming from?
Yeah, PFAS, as we've said previously, are everywhere. They're in all sorts of everyday products that we use, such as like fast food containers. They're in our cookware to make them non-stick. They're used in clothing to make them waterproof. They're used in clothing to make them stain resistant. We use them in the house in cleaning products. We use them in our personal care products like shampoo and dental floss, and they're in cosmetics as well. And also in sort of more households like commercial applications like paints and varnishes and sealants. They've been used in film forming foams. Because they're all in all of these products, it means that they're in our wastewater. They're part of the wastewater feed going into the wastewater treatment plants, and they're also in landfill materials. And because they're an issue in these places, they're an issue for wastewater treatment prior to discharge, and they're also in leachate that is generated by landfills.
And I know obviously you're a practitioner and you've been working with these chemicals in your kind of environmental consultancy roles. So I asked Dirk, I think, how big the problem is from your perspective, and you're in Australia these days. Where are you seeing it manifesting?
The main problem in my role as a contaminated line practitioner, and in the assessment of PFAS in particular, is the collection of representative environmental samples. As part of a PFAS investigation, we must conduct really rigorous quality assurance and quality control procedures. And these QA/QC procedures are designed to minimise any potential confounding sources and maximise the accuracy and precision of the data that we collect. One of those QA/QC procedures includes rinsate analysis, and this is where we pour deionized water over our drilling and sampling equipment prior to its use, typically 2 weeks before we go on site, and collect the water in a sampling vessel and then analyse that sample in a lab. This procedure checks for any pre-existing or confounding sources of chemicals. During one of my recent projects, we collected about 30 rinsate samples from the drilling equipment and the monitoring well installation materials such as the pipework and the bentonite pellets and the sandpack and our sampling equipment. And what we found was generally our pre-site work decontamination procedures were effective. However, the lab did detect PFAS in the rinsate samples from the outside of the monitoring well pipework, not the inside. And it took 8 different varieties of bentonite before we found one that did not contain PFAS. The reason for this and the cause of that problem was that the plastic packaging, which was wrapped around the outside of the pipes and in the bentonite bags, were providing that confounding source of PFAS. The fact that PFAS is ubiquitous also means that investigations and assessments conducted by contaminated land practitioners such as myself must be really rigorous, especially in the light of the really low screening criteria that are specified to assess our impact. It must be more rigorous than a normal investigation.
It certainly sounds from what you've just said and from listening to our guests on the main interview that it's a really complicated picture, and there's a huge amount of uncertainty, actually, the difficulty in measurement, but knowing what's out there. If I was to ask you, and I ask a lot of my guests this, if I was to give you a magic wand and ask you to wave it, what would you ask for with that magic wand? How would you solve this problem, Mark?
As we've said previously, PFAS are everywhere, and they're everywhere for a reason, because they're in lots of products that we use every day, and They're in lots of products we use every day because their chemical properties are really useful. They're useful for putting out fires, they're useful for preventing our food sticking to pans, they're useful for waterproofing and stain-proofing our clothing and carpets, as well as having this detrimental side to human health and the environment. So as a result, my magic wand would be to design a mechanism, whether that's physical or whether it's chemical or biological, which would effectively and rapidly degrade PFAS. And in doing that, it would not cause an environmental problem by using that technique or that mechanism, and it wouldn't produce any more toxic degradation products after you've applied it. So it would be a single hit and it would not cause any further issues.
Perfect, thank you. So it feels really live as a topic, doesn't it? There's a lot more to understand, but you've given us a brilliant summary, you've contextualised it really well, so thank you so much. But time has flown by, and here we are at the end of another episode of Planet Possible. Thank you so much for joining us. I really hope you found today's conversation insightful and it's given you something to think about in your world too. You can subscribe to the pod on your usual podcast player to never miss an episode, and we'd love to hear your ratings and your reviews too. I'm looking forward to sharing the rest of the season with you. So all that leaves me to say is a huge thank you to our guests today, Dr. Sarah Bwlb, Dirk van Look and Andrew Elphinston, and my excellent co-host Mark Challoner. That's it everyone, stay safe and I'll see you next time.
Planet Possible is produced by Bwlb. Bwlb Bwlb. The best ideas, the strongest content.